So a lot of what we do, especially in cold spray, thermal spray, diesel stuff has less to do with chemistry, so it's a lot of benefit. Waterborne coating, so this, again, it dealt with a lot of, when you talk about paints, right? When you do a lot of paints at your home and housings and stuff, a lot of them have to be promoted for waterborne coating. It's just more user-friendly environment compared to organic coating. So these kind of solvent is not only very friendly to the environment, but also to the body as well. Okay? So at the bottom of here, basically we're getting into what this is a small version of. My apologies if this figure is too small, but this is a version of a cross-section of a cold spray device, right? What you'll see. So when we talk about spray systems, it is often being kind of constituted or being, if you want to make a spray system, there's three key things you need to take care of. One is the spray control system, right? So you need to take fully control, or else you can't control what the point of the spray is. So second is the process parameters, right? What I mentioned, there's the temperatures, there's the pressures, how do you feed in powders and stuff, so that's the second one. And third is the materials preparation, right? How do you have the material ready so that you can have a successful coating from the spray system, right? So these are three key things when you talk about spray, right? So for the following slide, we'll talk about what the spray control system is. So when we talk about spray control systems, I listed all of these kind of main key for making your spray control. So first one is the gun, right? The nozzle, or whatever, well not whatever, what I stated, the spray torch, right? There's always the gun, right? So what the spray nozzle you plan to spray, right? The second is the feeder, so where you put your powder inside this mechanism or apparatus, right? So the feeder of itself, it does not only limit to powder, it can be wire, it can be liquid, or etc., right? So there's the feeder. And third is the media, right? So when I say the media supply, meaning that it can be, normally is like a gas form, so it can be nitrogen or argon, but at the same time, it can also be liquid as well, all right? So the media is to help you transfer whatever the spray coating material it is, all right? And then you have the labels of the robot, right? So if your lab is not as wealthy as it is, a lot of times you will use strategies as a label to do your coding. If your lab has enough investments or expenditures, you can have a robot to do your dirty job, right? So that's cool. The power supply, also the last power supply is the most important thing to have the total control. So the best, if you have sufficient power energy to control. And lastly, the control console, right? So this is where you control your process parameter, right? So these are the few, all the key things for making if you're designing a spray system, right? All of these you need to consider. All right? Does that make sense to you guys? All right, so let's get into thermal spray, or what we so-called plasma spray. So I believe this semester, there's also a graduate class that's offered in plasma spray. It is by our head of the department, Professor Guo. So he will talk about a lot about specifically plasma applications and theories and stuff. I'm not sure if that is offered in DMI or not. I don't think that's offered in DMI. But anyway, I want to briefly show you plasma spray, but also fall in the category of thermal spray. So this is plasma spray process. Key features that I want to point out, when you see a plasma spray, you will always see a cathode and anode. So cathode and anode meaning that you have a positive and negative. And then what's specialized is that you feed in this scenario, you put argon and then hydrogen inside a chamber that ionize this atmosphere. That's temperature is so high while you feed these powder, the powder basically get molten into liquid and then deposit onto the substrate. Okay, so when you see this is a typical anode cathode, you have an arc, is basically a thermal spray. Now, there's a lot of design, like, oh, can you have these kind of nozzle, but these are kind of the key features you see. Now, this schematic has taken the token to help us understand a little bit better from the material science perspective, is that when you spray, you can see you have a molten particles, right? So it's being dumped down. And typically feature when you see for thermal spray is that it's flat. So it's like a liquid form, like a ketchup or thing that kind of drop and then it's smashed into it. So think about liquid and the smash, right? So it's being splattered out like a flat thing, right? So a normal deposit you will see like a spray film over here on this over here. All right, so pros, again, you can see from through yourself. I do want to mention about the cons. The cons is always the most important, right? Because here's the funny thing is when you go buy something, the salesperson or the agent, when they often want to promote, they will always tell you the good stuff, right? The good stuff, no bad, perfect stuff, right? They don't tell you what's the cons about this stuff. Right? So pros meaning advantage, right? Hopefully, I don't know if you guys. The pros meaning the good thing, right? Cons meaning bad, 不好的. So pros is 好的，优点跟缺点. Okay? You guys know this? Okay. So the cons is that usually when you talk about thermal spray is you have high initial investments. There is a lot of investment you have to set up this thermal spray, plasma thermal spray. This is why when I started my research, I was hesitant to kind of go into. So when I say high initial investment is look at this design over here. It don't look simple, but a lot of things that you consume is argon and hydrogen. Right? So think about hydrogen. It's not very cheap stuff to get, and then hydrogen is highly dangerous. Right? It will explode. Okay, so it's not very, and then cathode and anode and arc, these are very consumable products that it's easily being depleted. So that's why the entire setup is very quite expensive. Not to say the safety concern and the regulations that you have to go through. So usually when a lab that has a single spray system, it is really quite a big investment. The complexities, as I mentioned, these are complexity, right? So it's not easy. Limited to flat or simple geometry. So when we talk about thermal spray, when we spray stuff, right? Normally when you see, I don't know if you today, maybe I'll try to find some film video for you guys to see, is usually when you do spray, it's on a very flat surfaces. You can also have some curvatures, but the thermal spray is very limited to a very simple geometry. So for those that have a very contour features, such as, I don't know, maybe like these kind of stuff. So when I say I want to spray this on this over here and this, it might be a difficult job for a thermal spray. Of course, you can use a robotic arm to help you control or facilitate a lot easier, but it does have some limits for doing such a thing. This is also very important, potential for oxidation. So when I say potential for oxidation, we also have to understand, on a previous slide I mentioned about there's two things when you do about thermal spray. One is you either increase the temperature or other you increase the velocity, right? So if you increase the temperatures, meaning that it's a lot easier when you spray the powder and get oxidized. Okay, so think about copper. When you raise the temperature, it's a lot easier to oxidize, right? So when we choose thermal spray as our applications, normally we won't spray materials that are easy to oxidize. Say, for example, copper, titanium, steel, metal, all these kind of stuff that are easy to oxidize is something we'd like to avoid using thermal spray. So because it goes with a high temperature. So what is the counterpart of using thermal spray if we want to use easily oxidized material? Cold spray, right? Because cold spray is cold and doesn't involve with temperature, right? So we use cold spray to spray material that are not easy to oxidize, well, easier to oxidize, right? And then surface preparation is another big thing. So a lot of my colleagues, or my research friends, when they talk about, hey, tin, my nickname is tin. So hey, do the spray, whenever you have to spray, easy, put powder spray, right? but it's not really that easy as you think. Surface preparations is a must when you do all these kind of spray. Environmental concerns is already mentioned, right? Does that make sense? So spray, thermal spray, this is another one, it's called detonation spray. So another AKA, so by the way, do you guys know what AKA means? Also known as, detonation spray meaning pulse spray. So pulse spray, pulse gas dynamic, so it's like an impulse. So it's like a frequency, right? So they give you an inject pulse, right? So they give you pulse, right? So that's what we call detonation spray. Again, this nozzle can be variations of different design. Over here, it has a feature of a somewhat similar structure of a cold spray, and then you have powders that's feeding inside from the conversion site. But interesting enough, the way that they do the detonation is by having an explosion chamber or combustion chamber over here. So think about your automobile car when you combust, right? You have these organic stuff in your combustion chamber. You burn up and then you push your car, right? So again, this is similar to that where you have a pulse dynamic in your code, right? So this is detonation spray, right? So these are pros and cons. You can go in and then review these. So again, the cons, I will only say about the cons, again, one instant feature that stands out is noise and vibration, right? So when you have pulse gas dynamic, it's very, very easy to see. Otherwise, these are roughly the same as I talked about plasma, so limit substrate compatibilities, surface roughness, if you consider considerations. All right? So, thermal spray. So here, HVOF. What does HVOF stand for? It stands for high velocity oxygen fuel. So you can do a same analysis. Right? Go to the next slide. Is HVAF. So A means air, and O means oxygen. So HV stands for high velocity. So high velocity, O stands for oxygen, fuel meaning that you're burning something in a combustion site, right? So you have HVOF and HVOF, right? So I also, I have done the liberty of taking this picture from online. I believe they did a great job to compare plasma gun with HVOF gun. So again, plasma gun is like kind of give you the distinct feature is that you have a cathode anode, and then a lot of times the powder doesn't play a role. The powder only, so all these anode catalysts help to generate high enough heat so that when you feed in the feedstock powder at the exit of this nozzle, it help to molten the powder, right? So the powder doesn't feed in from this side, okay? It's from the exit of the nozzle, right? So that's a very common simple spray system. What different from the plasma chamber we see from the HVOF gun is that now, instead of anode cathode, you don't have that. All you have is you have an ignition plug and you have a fuel, like your gasoline thing, right? And you fuel in oxygen. And then the ignite plug basically is like something for your car that it ignites stuff, right? In your car, you also have the same thing, right? You put the gasoline and ignite, right? So they have a boost and then fire up the energy so that it goes through. So this kind of design, sometimes there's some innovations or combined design that they also combine with a cold spray nozzle design, but it's not really a cold spray, it's just a similar feature. But you can see that when I say cold spray, there's a conversion and diversion, which I'll talk a little bit more later. But cold spray usually will have a conversion and diversion. But anyway, you will see these kind of inlet design over here. Now, over here, there's a couple of few comparisons. Hopefully you can go through each of these bullet points. I know it's really redundant and very tedious, but I think it will really help you. So this is mostly radial injection. Radial meaning, you guys know what radial means, right? It's more like a very wide area, while HVOF is more a specific designated area. So actually axial injection, so more a designated area, Pacific area, right? So it's not wide area. High kinetic energy, then plasma spray. Over here I just compare, all right, kind of plasma, and then dense coating due to supersonic impact with droplet. Okay. So moving forward, you can see this different zone. I don't think it's particularly important for you to recognize, but I know. Again, this is very intuitive. If you have a more closer zone or region, it's more hotter. We're at the wider range of places, you have less of heat that's being blown. All right, and then moving forward, the deposit over here would be deposit. So this is where the void is being built up, or the porosity being built up. For those that's not half, for those that are half molten or not fully molten materials, you can see this is where the porosity kind of builds up over here. So over here you can just go and read there's unmolten, semi-molten, and fully molten, right? So especially for those semi-molten part is actually where the kind of void is being built up. Okay? Questions? So thermal spray is the HVOF. Now the only difference is we're using air, right? So apart from using oxygen right now, we're using air. So air is, you might ask why we're using air, it's just more cheaper, right? So if you use oxygen, it's a lot expensive. So again, the same feature, you can see these particularly nozzle design over here, and then you have a very beautiful shock diamond that's coming out. But the only difference compared to HVOF, the HVAF is using air. Okay, so air, and now when I say air, it can be also nitrogen, it's just not oxygen. Okay, nitrogen, air. So I put two features. This one is air, this one is putting nitrogen instead. Questions? All right. You know, this is a side thing I have to say. You really have to be very passionate about doing spray so that you don't get overworking all of this stuff. Okay. So I understand a lot of people looking at this, they start falling asleep because, man, God, how much nozzle is going on? I guarantee you, there's two more going on, and then we're ending, and we're moving forward to the next content. All right. So again, like, if you're about to fall asleep, just tell your inner conscious mind, we're almost there. There's no more nozzle going on. Okay. All right. Thermal spray is the HVOF, and actually I recently did a organization for you guys. The working principle, as I expressed, one is oxygen, one is air, right? So you can easily figure that out, right? Second, the coating velocity is, I think this is also very easy for you to understand. For those that use oxygen, meaning that it's not easy to combust, right? Oxygen helps to combust, right? So the velocity is a lot faster or higher, right? So you can see HVOF as a relatively higher than HVAF, okay? So it's a lot higher, 1,900. Does that make sense to you guys? So we're using oxygen, right? Oxidizer, of course, oxygen and compressed air. Coating qualities. Of course, you're using HVOF, it has a higher quality compared to HVOF. Okay, the detail over here, you can kind of read this detail. But one thing I would say is that I'm not trying to demolarize or kind of downgrade HVAF. I'm not saying that. I'm just saying that, compare each of these techniques. There's some content pro, right? So at the end of the day, you have limited resources. Of course, you can use HVAF. You can still reach the quality you want, right? And then the material compatibilities, of course, there's wide range. Materials include metal, ceramic, carbide. It's also the same wide range, right? Does that make sense to you guys? Okay. So you might ask me, is like, it seems somehow this is like great, HVOF. We can just use this into whatever we want, there's a ceramic, let's spray ceramic, there's a metal, we use it. If it doesn't coat, we just increase the pressure, we increase the temperature, right? If it doesn't, we'll do that, increase, and then eventually we'll pack it. This is where the research come in, is that if you can have a minimum of your materials consumptions, and if you can know that number, it will help you save a lot of resources than doing a lot of try and error, right? So you can, if you start looking, end of this class and start going on the website and then review a lot of the spray system and and then they will throw you tons of manufacturing process. All right. Hopefully, you guys are, a lot of you graduate students, PhD and master, right? For those master students, maybe you have undergrad sitting over here. You, at a certain point, you might realize a lot of times you are in the lab, are spending tons of time doing trial and error. Right? If you do centering 1,000 and then 11550, or you add this material 1%, 5%, 10%, or 20 and 25%. So isn't that the same as this one, like what you do? And my advice for you is that the contribution from your side is that you really need to think about what is the relationship, and is there other tools to help you to find some predictions to allow you from avoiding doing a lot of try and error. So I see a lot of master theses that sit in your defenses. A lot of times is, to be honest, it's a try and error. Right? You did this and then in conclusion you find out this is the maximum performance, right? So somehow the lab has HV or F, and then you want to spray this, you try to maximize, all the process parameters to find if this do its coding or not, without finding what's the physics behind. So hopefully this can help you and give you some thinking about it, right? So thermal space, I think this is 1, 2, 3. I think we have three more nozzles going on. Are you guys excited to see these nozzles? Do you guys feel passion within these nozzles? Yeah. Let me help you answer from you guys. We really care less about these, right? Exactly. I really care less about. But the thing is, we need to have some idea when we see these, right? So again, this is a spray introduction. So of course we need to go through all these. So thermal spray, we have wire and powder arc spray. So majorly the difference over here, you can see when we talk about wire arc spray, basically you have known as a twin wire arc spray. You have a positive and negative that's charged upon these wire, and then fill in the nozzle, and then being combustible, going out into liquid form and deposit. So this is the wire powder box. So you can also feed in powder from each side, positive and negative. And then thermal spray, so this is just you can call it flame powder or wire spray. So this is just, there's no arc going on, or positive, negative, or electricity. You're just burning the powder, okay, into a molten form. So you're feeding the wire, and then you have a combustion center just heating it up, and then putting into liquid. So this is flame powder or wire spray. Alright, so over here I also organized the wire arc spraying and wire spraying. You can have a look by yourself. I won't go into detail. Alright, so thermal spray. So this is kind of the same as it's the same as the pre-film when I say thermal plasma spray. Plasma arc spraying, what really a little bit different. You have again positive, negative, and then plasma gas feeding in, and powder coming from the outlet, and then the spray. All right. Any questions so far? All right, good. So we're moving forward into cold spray technology. We'll spend most of the time to talk about this. So this is briefly I'll spend to talk about the mechanism, and as a material background, we always like to emphasize the process and the structures property relationship. Right? So I'll spend a little bit of time to talk about the structure property relationship and what's the motivation behind it. Okay. So I'm using CFRP as an example why we're using cold spray. I'm not saying that there's a lot of material, but I'm using this as a why. Okay, why are we using cold spray? Okay, so I'm not saying cold spray can only do metals or polymer. I mean, there's a lot of variation, but I'm just using CFRP, which stands for carbon fiber reinforced polymer, as an example for kind of arousing you guys' motivations and then why. All right, so CFRP, if you don't know, stands for carbon fiber reinforced polymer plastic. So it's mainly used in structural component aerospace, automobile infrastructure, and sports. So I listed all these pictures over here. Right? So there's, in research-wise, there's a lot of kind of need for lightning strike or electromagnetic interference, all these kind of need going on, industry going on. So when you do CFRP, I don't know if you know, CFRP, as I mentioned, is a lot of used in aerospace, right? So when I say aerospace, it's like commercial jet flying in the air, flying in the air. So when you fly in the air, there's always some lightning strike going on. Actually, there are. And for CFRP, right now we're promoting 2050 carbon emission. Right? So usually nowadays all these commercial flight actually change using CFRP material, which is lighter and half the strength. So right now there's a lot of reasons that deal with lightning strike or EMI. So at different level, there's the metal threads for your metal lines and then conductive polymers. There's a lot of ways you can do to increase its electric conductivities. These are a common method you can do: metal threads, metal line, and then polymer-based film that you can put. But spray metal on the surface of the substrate is an alternative solution. So this is why course we come into a major play right now, at least in CFRP. So CFRP stands for carbon fiber reinforced polymer. Okay, so this basically bring up a new research territory compared to a traditional what cold spray is. Alright, so traditionally when you talk about CFRP, if you want to increase its electric conductivities, common ways you put metal thread, or you put metal lines or conductive polymer onto the CFRP. But comes along cold spray, it helps to leverage that, a lot easier to increase, right? All you have to do is spray and done, right? So this is the motivation why we're talking about cold spray. Does that make sense? So I'll quickly go through all this. VCR for cold spray is around 300 milligrams. So over here, this is when you want to spray on CFRP, there is a wide range of different substrate. You can use different feedstock powder. We won't go into this. Quickly skip this. So how does cold spray function? So how does cold spray work? So originally, cold spray was discovered by the Russians in 1980. The way they found this out was during the Cold War, when there was a compete between the United States about who is the first one to go onto the moon. So at that time, they want to come up with a very strong combustion engine so that they can push the nozzle out from the Earth because of the gravity. So what happened at the time in engineering, Russian engineering, what they do is they built this nozzle. This nozzle is a conversion diversion nozzle. So conversion and diversion, aka also known as the lava type nozzle. And accidentally is the engineering at that time, instead of putting the fuel inside this rocket engine, they put powder inside while it is being combusted, as flow. And there it goes, the powder flies into the nozzle and hit onto the wall and attach onto the substrate. So this is where the boost plate of cold spray. Right? So everything is accident effect. Okay? So I also want to mention is that cold spray is a similar type of your engine nozzle. Commercial F-16, F-18, any Airbus, commercial flight nozzle, when you see these nozzles on the wings, they're also made of convolution diversion nozzle. That's not surprising when you want to reach a supersonic speed. This is a very typical nozzle. So what you're seeing right now is just a small miniature version of an engine nozzle that's demagnified into a more smaller feature where right now it's displaceable and handheld portable on your hand. So it's cold spray. Alright? So these are a few things. High compressed air flow through your channel. Cold spray is effective by using solid powder flowing through your channel through a design, as I expressed. The particle reach a supersonic speed while exiting the nozzle. So this again, when I say supersonic, meaning that it's Mach higher than 1, I'll kind of I actually have a lot of notes we're about to take later on throughout this slide, but I'll explain the definition of block and stuff. So it also depending how you design this nozzle. So how do you reach a supersonic? Depending how this curvature of the nozzle, how do you have designed this nozzle that allow your particle to reach a supersonic speed, right? So this is all to do with some fluid science. We'll talk about that a little bit later on. So cold spray is relatively low temperature compared to thermal spray. In the cold spray system, it's basically separated into different categories, 3 categories: the low, high, pulse gas dynamic. So low pressure cold spray and high pressure cold spray and pulse gas dynamic. So pulse gas dynamic is what I just mentioned, is similar to detonation spray, right? You have pulse going on through, right? So either through a combustion chamber or other ways. Low and high pressure, basically depending on where you feed in your powder. If you're feeding powder from your divergent side, that's basically a low pressure. And if you're feeding from your convergent side, that's a high pressure. Right? So the higher the pressure means that you have a higher chance of depositing your particle. All right, so advantage of cold spray. This is the advantage. A lot of things that the cold spray have. One of the things I just want to highlight is compared to thermal spray, as I expressed, is that it's very good for those materials that are easily oxidized. So copper, for example. So you should remember that when people say, hey, you want to spray copper? Please use cold spray. All right. So on the right hand side is I listed there is a lot of research or resources that's being poured into this area. Right? So I'm not doing a research that's about to die. So there is a lot of growth, especially in Europe and USA. Consider, you can see on over here, cold spray, it's actually exponential growing from 2002, 2012, 2016 right now. It's continued to grow. Right? So this is, although this is not a new technology, but at the same time, there's a lot of growth going on. Again, this is what I mentioned, particle velocity, particle protrusion, and etc. Okay? Good. All right, so important factor in cold spray, material-wise, is the powder substrate, size fraction, powder, and then etc. Gas, type, pressure, temperature, velocity. And then equipment, as I kind of stated in the previous slides, there's different systems that make this up, right? Okay? Good? All right, so getting into this is where we're going to take some notes. Unfortunately, I cannot write on my iPad, so I rely on the blackboard. All right, so this is a very common finite element analysis of the cold spray process. You can see the flow simulation on the left-hand side of the cold spray nozzle. Particularly when the design is correct, which I'll have a full of notes for you guys to copy. If all the designs are correct, you will have reached a Mach equal to 1, particularly at the throat system, so that once it's exiting the nozzle, it will retain a high supersonic speed exiting out. So over here, again, this is a temperature. You see some kind of a diamond feature going on over here, and then the particle velocity, the gas velocity, basically kind of up goes as the distance increases. Right. So here are some notes I need to copy. I have not used chalk for like a decade already. 哎，我这边写你看得到哦，你应该是 right over here. Right, good. So this is conversion. Actually, can you guys see blue? Can you guys see this color at the back? Blue. Can you see it? Too dark. Too dark. Okay. I'll just use orange. Is this better? Okay. Yeah. So you guys continue to copy the notes. So there are 7 cases where you design a cold spray nozzle. So first is no flow. Alright, each of these cases we'll talk about. Second is isentropic. So when I say isentropic, it's basically we don't have any loss due because of frictions. Are consumed throughout. Third case is choke. We have a choke. That's in trouble. Fourth case, we have normal shock, nozzle. So, fifth is normal shock. Exit. Down. And then 6 is move expand. And 7 is over expand. Right? You guys see? Okay.你去那个办公室的话，就是通常在电脑就是教授你是找谁啊？王小姐吗？
你的王小姐是主要管的。
你会像王小姐说，因为那个 HDMI， 它是 HDMI 接这个什么 USB 的那个什么 Thunderbolt 转接线。这是3.0哦。Type C 啊，对 Type C 啊 ，Type C 就是连接到电脑 HDMI 有问题。然后看他是要叫还是要用对方的，再帮我问一下。好，下次就就是别的老师他也有遇到，
好，
如果换的换教室，没错，这第2堂到底3个10分啊？
应该是。
对，你们那个国际就是国内是拿那个你们那个选那个题目啊，尤其不是我们实验室，如果你是就别的实验室的啊，或是你是大学生，你可以下课来跟老师稍微谈谈你要学什么， 凹钢柱底下哦，不要镶东西，对吧？你能找老师谈一谈，好不好？
What's P?
Pressure. Pressure. P is pressure. Yeah, stagnation pressure. Static pressure. Static pressure. So P will be used in pressure. Yeah, I'm terrible at writing. I apologize. Yeah. So, 哪一个不是很清楚？我知道有那个什么 O 啊 N 啊 R 那个，如果他们知不道，有人说。Yeah. So, while you guys are writing down, I wanna. I don't know. So, I give you some cases of, well, not some cases, like every cases you can come up with your design and conversion, divergent also. Okay. So what you're seeing right now, this is a conversion divergent. So meaning on the left hand side, the conversion, on the other side is the divergent. So when you design, there's always at the middle, there's the AT. AT meaning that's the area, T means the throat. So the throat means the neck, the throat, okay, the neck. So P not means the stagnation pressure. You can think about that's the reservoir, the combustion chamber, the reservoir, right? And then, so when you go in, any of these areas, like X is from, I want to give you the coordinate system. So this is the x-axis, right? The pressure over here, the P, can be anywhere depending on what the X value that I gave you, okay? And then you have P sub E and A sub E is the pressure exit. E meaning the exit, so exit pressure, the exit plane, and then the back pressure, meaning that's, again, you can think about it as a reservoir use, back pressure. And then this is the area, okay? So they are undefined. So there are 7 cases. The no flow, and then the second is isentropic, subsonic throughout, and then you have choke isentropic and supersonic flow, depending on there's 2 solutions for this. And then you have normal shock in nozzle. So, and then the 5th is normal shock and nozzle exit. And then the 6th is overexpand and then underexpand. So when I say shock, what does that mean? When I say shock is, you normally see like diamond shape, right? You got kind of think of this fuzz. When I say shock, what does it mean? Like when you have a nozzle like this, right? When your nozzle is flying out, and then you have these kind of turbulence, like a very beautiful turbulence that's coming out. So these are shock. That's what we call a shock. Okay, diving shock. So normal shock, and then overexpanded and underexpanded, right? So these are the 7 cases. I'll kind of elaborate that a little bit more after the next class. Did the bell ring? Let's have a recess, okay? All right, so for those that have not ever come and talked to me about the report you plan to write, or like what sort of topic, if you guys want to talk today, great, or use any time for the following week, okay? So I don't want to let you guys like wonder your wood and have no idea what's going on. 就是你们有问题的话，趁这一节，或是下一节，或是下一节赶紧问，好不好？不要害怕，哦 ，OK 吗？All right, so let's have a recess. We'll be back.